Okay, I'm going to give you a little bit of something that you can work on in class today, and then something that you're going to be able to work on in class tomorrow. Everybody's to this page in their worksheets. Okay, so part of what you want to be able to do is you want to be able, so last week we talked about matching graphs of functions and their derivatives. You'd also be able to like to sketch just a general graph of a derivative as well. This is my original function, and I would like to sketch the graph of the derivative. Can anybody tell me something, anything about the graph of the derivative? It's 0 at -4. So the first mistake on this worksheet, I'm sorry I didn't fix it, but this technically shouldn't say f of x. Technically, it should just say x. So for an x value, as Bree said, of -4, the derivative value is 0. She's correct. So she sees right here at an x value of -4, I have a slope of 0. And at -1, I also have a slope of 0. I apologize for the horrendous graphs. If you could do your best to work with the situation, I would appreciate it. Okay. Now, tell me something about the derivative here. It's positive. So before that, the derivative is positive. So I'm just going to place positive there. Tell me it's positive beforehand. And it's negative in between those values. And then after -1, it becomes positive. So nobody said the thing that I wanted to hear. What degree equation is this? Third degree. So therefore, the derivative will be second degree. So what should the derivative look like? A parabola. Question. So they just remember from last year that that's a cubic shape, that's third degree. So first degree is like that. Second degree is like that. Third degree, fourth degree, fifth degree. So, so on and so forth. So people just kind of start to memorize that. The idea is here in this situation, you have 2 bumps. So one will be removed. So this next will have 1 bump. It'll just be a parabola. Okay, so I plot at -4, I plot 0, 1, 2, 3, 4. And at -1, I plot 0. Do I start above or below the x-axis? I start above because it says positive, and I drop below. A lot of times people ask how far below. Don't worry about that right now. This is just a general sketch of the derivative. Okay? Learn about what? Eventually, yeah. So there is a very specific graph. We're just not really that important at this time, okay? So I'd like you to kind of get your feet wet and try a couple more on this front side, okay? Go ahead, try a couple on your own. Okay, please flip to the back side. Please flip to the back side. Okay, I'd like to do 2 problems here with you. Can somebody tell me something about the derivative for number 9? Very good. So at 0, it does not exist. So you cannot determine the slope at 0. So therefore, the graph of our derivative will be discontinuous at that spot. Okay? Tell me something about the slope before that. It's negative, and in fact, it has a value we actually know. Like, people have been asking, like, how high or how low do we go and why? Well, it's really hard to tell. So we've been making general sketches. But here it's very easy to tell that the slope is -1. So the slope is -1 before that. How about after that? It's +1. So therefore, I'm going to draw a line of -1. So it's just going to have a height of -1. And at 0, I have an open circle. And then I pick up with an open circle and an arrow to the right then. So I would say that the slope here is -1. Okay. Yes. So that's what we're going to do next, okay? And then I'm going to let you guys be for a second, okay? Shh. Okay. Let's look at number 10. Okay. What can you tell me definitively about the graph of number 10? Okay. The slope is always positive, except so. Think about this. The slope is always positive, so the derivative should always sit above the x-axis, except there's one spot where the derivative is not positive. And where is that? At 0, what is the derivative there? It's a vertical tangent, so therefore the slope does not exist. So what I know that is at 0, for an x value of 0, the derivative does not exist.
Oh, because it's like a vertical tangent?
Yeah. Yes. So if we consider that, how would you describe the slope here other than saying it's positive?
It goes more and more.
It's positive, but it's small, right? It goes from small to very large. So it goes from small to very large. How would you describe the slope from here to very small? So large to very small. Now, as you guys consider these types of problems, I can't encourage you enough. We are past the time of looking at something and being able to figure it out in 3 seconds. These are not necessarily easy. A lot of people have questions on these, and that's the nature of the calculus. So I'm going to give you a couple minutes to look at a piece or two of these, and then we have to move on to the next piece. Okay? So a couple. Okay, last question, and then please. Okay, turn in your notes to this section. Okay, we move past the graphs. We're moving to this section, these 3 problems. Find the derivative of the following functions, so on and so forth. Great. So now what we want to do is we want to look at the limit as h goes to 0. We want to find the derivative. So we've been able to sketch derivatives of graphs. We're going to do the same thing, except instead of sketching the graph, we're actually going to find the derivative. So now we're going to work on an algebraic approach. And the derivative is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And so I have 3 challenging problems here. I'd like to start with an easier one. Can we start with an easier one? Okay. So we're going to start with letter D. And we're going to say f of x is equal to 2x minus x squared. Okay. What? If you want to, we'll write it again. It's on the other side, but that's fine. So if something says to find the derivative, that's what we need to accomplish, is to use that thing right there. Now, hopefully later on this week we can get to what we refer to as kind of like the shortcut to some of these processes. But right now we're gonna execute this thing with these type of functions, and we start with letter D. Everybody got that? Okay, so that means that f prime of x is equal to the limit as h goes to 0 of, and let's see what the rule tells me to do. It tells me to first take x plus h and plug it in for x. So anywhere you see an x here, I plug in an x plus h instead. So I have 2 times x plus h minus x plus h quantity squared. What does the rule tell me to do after that? Subtract f of x. So minus the quantity, good, all over h. What's your question, Bree? So 2 comes from this. You good now? Okay. Now the rest becomes a process of just algebra. I get the limit as h goes to 0 of, what is this first part? 2x plus 2h. What do we get if we square x plus h? X squared plus 2xh plus h squared. But we're going to distribute a negative. So minus x squared minus 2xh minus h squared. You okay with that? And then what are you going to have after that? Good. And that's all over h. Okay? So, what do you notice? Yep. Well, I'm sorry. I put a 2x there. That should be a 2h. Sorry about that. So the 2x's cancel, and the x squareds cancel. In fact, everything that doesn't have an h cancels. That should be repetitive from last year. So I get the limit as h goes to 0, and I can factor an h out of the top. What are you left with when you factor an h out of the top? Good. All over h. What happens now? The h's cancel. Can I now plug in 0 for h? And when you plug in 0 for h, what happens? Yeah, that piece goes away, and so you get the derivative of the function is 2 minus 2x. That is the exact derivative. That will tell us the slope at any spot. So for example, suppose you're like, what is the slope at an x value of 3? What's the slope at an x value of 3? Just plug 3 into there and you know it. And suppose you want to know, well, I want to know the slope at x equals -1. Well, just plug -1 in there and you'll know it. So this will tell us the derivative at any spot that we want. Super useful. We good with that? Ready for a slightly more challenging example? Okay, let's look at letter A. I would like to find this derivative. Now, anybody know the domain of that function? X can be 2 because 2 minus 2 is 0. X has to be less than or equal to 2. If you were to graph this, does everybody agree that it looks like that? So therefore, it would be from -infinity to +2. We should find the same domain with our derivative. Not that you have to do that. I just want to show you how it works out. So let's try this one. The derivative is equal to the limit as h goes to 0 of, and what do we do? Good. So if I plug in x plus h, I will get the square root of 2 minus x minus h. Right? minus what? The function, so square root of 2 minus x, all over what? H. Now, it worked out, yes.
So pretty much. Oh, I get it now. Okay. So anything that has x in it, plug in minus x.
Plug in x plus h. Yep. Okay. So as you look at the previous problem, notice how we were able to square it and things canceled out and went away beautifully. But in this problem, that's not going to happen. Anybody know what we do to kind of free up our x's and our h's? Multiply by the conjugate. Excellent. So the conjugate is the square root of 2 minus x minus h plus the square root of 2 minus x over the square root of 2 minus x minus h plus the square root of 2 minus x. Looks kind of bad, doesn't it? Yeah, it does. I'm going to tell you that the top ends out working out really nice. The bottom is not quite as pretty, okay? And so we have the limit as h goes to 0 of, what are you going to get here? Good. Middle's going to cancel. It'll be a negative 2 and then a plus x when we distribute the subtraction sign, right? Okay, so we get a minus 2 and we get a plus x. So we're going to let that be. The bottom, you just have to allow it to be kind of its ugly form. H times parentheses, that beast. So square root of 2 minus x minus h plus the square root of 2 minus x. What happens to the top? 2's cancel, x's cancel, and then the h will cancel at the denominator. So what value are you left with in the numerator? Good. So I'm going to cross it off, leave me with a negative 1. So I'm going to write this out so people can see it. So I'm going to write out this extra step. Limit as h goes to 0 of negative 1 over the square root of 2 minus x minus h plus the square root of 2 minus x. Those are almost the same things, aren't they? Can we now plug in 0 for h? Yeah, I can plug in 0 for h. And when I do, notice how I plug in 0 and it goes away. Are those now the same things? So there's 2 of them. So negative 1 over 2 roots of 2 minus x. There's 2 of them now. I plugged in 0 for h. This is the derivative. This is f prime of x. Now, part of what I want to show you that's pretty cool is this. People remember how the original function, it looked like that? And you said the domain was from negative infinity to positive 2. Agreed? But you can't take the derivative at a corner, can you? So look at how the derivative shows up. Its domain, again, is from negative infinity to 2, but what value can't you plug in for x? Yeah, you can't plug in the spot where you get the derivative at a corner. So it matches graphically with what we have algebraically as well. One more for today. We're not going to do C today, but we are going to do B. We okay? Limit is h goes to 0 of what? What do we got in top? X plus h. Okay, so I plugged in x plus h in the top. Now what? You always plug in x plus h because this, what's that?
Oh, I know.
because the rule says the limit as h goes to 0.
So you plug in x plus h. The first part, you plug in x plus h whenever you see x.
Yes. That's what this means. This means you plug in x plus h for that piece. Yep. What do we do after that? X over x minus 3? All over h. Yes, common denominator is very good. So you have to multiply this side by
x plus h minus 3.
I can do it.
and then
I can do it.
I will say, folks, I am trying to prepare because this test does not go as well as the first test. So, yeah, oh, without a doubt.
This looks like we did last year.
No, I'm just trying to prepare us because I know we're getting stressed out. We've all of a sudden realized we've got 5 AP classes and that whole business, but I've still got to teach calculus at the end of the day. So this is a tough test for people, without a doubt. Yes. I don't. We got to see how much more material we could cover. So we got to get through 3.3 yet. We're at 3.2 right now. Okay. So limit as h goes to 0 of, what do you have in the top there? X squared plus xh minus 3x minus 3h minus x squared minus xh. Okay, let's pause right here. I'm distributing a negative x through. Negative x times x is negative x squared. Negative xh plus 3x. Okay, before we start crossing stuff off, divided by? Nope. X minus 3 times. Yeah, I wouldn't multiply those denominators together. I don't think that helps us. All over h over 1. Okay? Now, it's like it's Christmas because we get this gift of just canceling. What do you notice cancels? X squareds cancel. Negative 3x and positive 3x cancel. The xh and the negative xh cancel. So I get the limit as h goes to 0 of negative 3h over x minus 3 times x plus h minus 3. And then instead of dividing by h over 1, I could what? Multiply by 1 over h. And when I multiply by the reciprocal, what happens? The h's cancel. So we have the limit as h goes to 0 of negative 3 over x minus 3 times x plus h minus 3. Don't those look like they're similar?
Oh my gosh, you put in 0 and the h goes away. Oh my.
Put 0 and the h goes away.
3 over 2 times 1 x minus 3.
No, x minus 3 squared.
X minus 3 squared, that's what I meant.
Because you're multiplying them. In the previous problem, we added them, so we had 2 of them. But in this case, we're multiplying them, so you get the derivative of f of x is negative 3 over x minus 3 quantity squared. Just so we see, if you guys could turn your attention to the top, what number can you not plug in? You can't plug in 3, so everybody agree that you cannot take the derivative at 3, it's discontinuous? Sure enough, as you look in the derivative, the one number that you can't plug in again is 3. So the domain of the original function should pop up accurately in the domain of the derivative as well. So, good work. Yeah. So, let me show you what you guys have. Number one, you have, so right now, you guys were working on this piece right here, right? This is the graphs of derivatives right there. The one after that is the formal definition of the derivative, and that's what we just did right now. So the plan is that tomorrow you would be able to have time to work on those pieces, okay?
When you multiplied.
You have, yes, you have, yes. Yep. The last one's optional.